Hi everybody, welcome back to the Feynman technique. So today we're going to be solving Raabe's integral, and it's spelled R-A-A-B-E, not R-O-B, although it is pronounced Raabe. Um, so this is a notoriously difficult integral, but using the techniques and formulas that we've already discussed recently on this channel, this is actually not that difficult to solve. Um, so First, let's make the substitution that u is equal to 1 minus x. All right. Well, that's dx is equal to negative du. Our bounds switch from 0 to 1 to 1 to 0. And now we have this integral, and we can distribute that negative sign and switch the bounds. So now we have I is equal to this, but also we have our original definition of I. So now we have 2I, or I plus I, is equal to the two versions of it we just found. One is our original, and one is with the substitution applied. All right, so now we have 2I is equal to this, and we can use properties of logarithms to just bring those into one single logarithm. And now you'll notice that we can use Euler's reflection formula directly on that. So let's go ahead and do that. And now we have that 2I is just equal to this integral. And this integral is actually not that bad because we've actually solved the one on the bottom here, the natural log of sine pi x from 0 to, well, we've almost solved it. We solved a very similar integral, and solving that one will just be a simple substitution. All right, so let's continue. So 2I is equal to this, and now we can break this up into two separate integrals using properties of logarithms. So now we have 2I is equal to this. This one is very easy. That's just going to be natural log of pi. And this one we'll have to break out King's property to solve. So this is just evaluating that first simple integral. It equals natural log pi. So for our second integral, let's make the substitution u is equal to pi x. So dx is 1 over pi du. All right, our bounds go from 0 to 1 to 0 to pi. All right. So bringing out that 1 over pi from our differential, and now we have this integral. And now here's kind of a cool visual trick to break this one up. Instead of using algebra or substitutions or splitting the integral or anything like that, we'll just visually see that this integral has got to be twice the integral going from 0 to pi over 2. Because look at what sine does. Sine goes up and then down, and it's symmetric about the line pi over 2. X is equal to pi over 2. So just think about it. If we took the natural log on any one of these values on this side, it would equal the corresponding natural log of whatever we get on this side. In other words, basically the entire area under log of sine u from 0 to pi is just twice what it would be from 0 to pi over 2. All right, and you can also show that just by splitting and doing a substitution. All right, so now, well, let's see what we actually get. So now we actually have this integral. Now, the integral that we've actually already solved is this one. We've solved that one on the channel before, and it equals to negative, let's see, what is it equal to? Yeah, negative pi natural log 2 over 2. All right, so simplifying that, we can see that that's just going to equal negative natural log 2. All right, so that's what our 2i is. Our 2i is natural log of pi minus a minus natural log 2, or just natural log of pi plus natural log of 2, or simply natural log of 2 pi. Then dividing both sides by 2, and we have the value of our original integral. And that is 1/2 of pi natural log of 2 pi. All right, guys, hope you enjoyed that, and we'll see you next time.